Okay, welcome back. So I'm just picking up where we left off in the last video. We're going to find the dot product between these two vectors. So I'm going to call this one vector A and this one vector B. And if I were to graph them in space, this isn't strictly necessary, but I like to know kind of what I'm looking at. So 1, 2, 3, 4, 5. All right, so vector A is 3, -2. Looks like this. That's vector A. And vector B, sorry, that's not a very good drawing. Let's try that again. There we go, that's better. That's vector A. And vector B as this guy. And all I want to do is find the dot product. So I want to find A dot B. And that's just the x components multiplied together. So 3 times 5 plus the y components multiplied together, which is 15 minus 2, so that is 13. And that is the dot product. Okay, so now let's suppose we've got a slightly different question at hand. And I'm just going to copy over my dot product definition so I keep them fresh in my mind. So suppose I've got an object and it's being acted on by two vectors. One going straight horizontally to the left with a magnitude of 7, and another one operating upwards with a magnitude of 6 at an angle of 30 degrees with the horizontal. And we want to find the dot product. So let's label this one vector A, and this one, no, let's do this one. So let's call this guy A, this guy B. Now, I can do this two ways. I've got enough information to get the component form, right? So I could easily write vector A in component form as -7, 0, and vector B as 6 cosine 30 degrees, comma 6 sine 30 degrees. And I know enough to figure that out, right? Because I know the cosine of 30 degrees is root 3 over 2. So this would be 3 square root 3, and the sine of 30 degrees is 1/2, so 3. And we could do that. We can now write that A dot B is equal to -7 times 3 square root 3 plus 0 times 3. Which would be -21 square root 3. Yes? Okay, there's another way we can do this though, because we also know that we can find the angle in between these as 150 degrees. Yeah? And so we also know that A dot B is equal to the magnitude of vector A. So I'm using now my second definition. So the magnitude of vector A times the magnitude of vector B times the cosine of the angle in between those two vectors, which is 42 times negative square root 3 over 2, which again leads us to negative 21 square root 3. In either case, we have found the dot product and gotten the same answer using both methods, and that is what we should do. Okay, so the next thing that the dot product is good for, as I said in the introduction, is determining how much of a vector actually, so it's called a projection, and we're going to talk about this in the next video, but I want you to think about this problem, and then we'll solve this in the next video. So we've got an object being pulled up a ramp. And I'm going to give you the specifics in a second, in the next video. But so we've got this box being pulled up this ramp, and we're pulling it at that angle. So we aren't pulling it directly in line with the ramp. And if you think about how you generally would pull us, for example, a wagon or a cart up an incline, you'll understand. So the question is, how much, or what portion we can so how much of the applied force is actually going towards moving the object up the ramp. All right, the dot product helps us out with this, and we'll come back and talk about this in a minute.